let's make it. Let's build it and see if what we have designed theoretically, if it also maps on what we are going to measure. Otherwise, it would be useless. And here you see my piece of art. And here, this very small black thing below this resistor is a SMD operational amplifier. This is for one phantom zero, and somewhere else the other phantom zero, I think, is here. Without compensation, we have the ringing. It's less than predicted by the model, but still visible. And the nice thing is that this ringing is not at all predicted by the micro model of Texas Instruments. So our modeling was more accurate than that. With one phantom zero, here this 27 ohm, you see the effect of the ringing already. The ring is gone. And with the next one, this is only with capacitor. You see it damps, but the ringing is still there. It's not so effective for the ringing because the ringing was the high Q in this output circuit, and I reduced the Q also with this impedance, with this resistance of 27 ohm. So this is both of them in it, and you can check the step response, the peak-to-peak, and the drive capability in the overdrive recovery. And you can see we can easily drive we can do 4.98 volts peak to peak. That's almost the power supply range, peak to peak on this capacitive load. And here you see the Bode plot. I was a little bit shaking when I made the picture from my network analyzer, but you see the minus 3 dB is at 668 kilohertz, and it was the poles, maybe you remember something like 666 from our theoretical model. Then the noise. Unfortunately, my spectrum analyzer and network analyzer is not sensitive enough. I needed to have an extra preamplifier to measure the noise, so I did it with the oscilloscope. It's not the best technique, but I first shorted the input and measured the noise of the oscilloscope by means of a histogram. So this is the noise of the oscilloscope itself, 83 microvolts RMS here. And here you see the output noise of the amplifier is much more, so I can ignore the noise of the oscilloscope. And with that, now the question is, what is here? You see, it is measured over 11 megahertz, but the amplifier, of course, has a low pass characteristic that is limited to 660 kilohertz. So over the frequency band of interest, even if I take, let's say if I estimate that the noise bandwidth will be about pi over 2 times 660 kilohertz, then I will have about a noise figure between 2.3 and maybe 2.7 dB, and 3 dB was allowed and 2.4 was calculated. So you see, it's really good in the range that we expect it to be. So the amplifier complies with the requirements. The SPI simulation with the TI micromodel, and I will show them later, did not show small signal instability. The modeling of individual performance aspects, as we have done in this course, seems to be a very successful approach to do a step-by-step design.